Welcome to our first webinar on applications. Today we will have the first topic, strength of HPTLC for analysis of natural products, using cannabis as an example. So during the webinar you can enter questions to the chat box or send them afterwards to my email address or in general to request@camag.com. The content of today, our agenda is we will first see the introduction, then talk about the analytical task, especially in cannabis testing. Limit test and quantification will be explained, then how to perform identity testing and the perspectives. So now about some general aspects. HPTLC is the preferred technique for natural product testing if either it's easy to perform and easy to evaluate, or if it's faster, if you have less sample preparation, or if you can run a lot of samples in parallel, and if it's cheaper, so if you have low running costs. So in natural products, HPTLC is all of those aspects. It's easy, fast and cheap. For cannabis, there are different classes depending on the use. We have the industrial hemp that is used for textiles, for food industry. We have the medical cannabis, and we have the illicit drug. Then we have different analytical tasks depending on if we want to analyze different plant materials or finished products or follow the different process steps. If we look now here on this top, we have whole plant flowers, dried flowers, powdered flowers and dry extract. All of those sample plant materials are very complex, and there especially HPTLC is beneficial to test the identity. Then we can have different finished products, complex product like a cannabis tea for example, or other food, dietary supplements, etc. Then we can have processed extracts, capsules, tinctures, oils, etc. We can have isolated class of compounds, different cannabinoids, and we can have the purified single compound, for example the CBD. The degree of complexity is decreasing during this different processing, and the degree of purification is increasing. So HPTLC is especially beneficial if we have to deal with complex samples. So the more we get on this side, the more HPTLC is the method of choice. For these plant materials, we have mainly the issue or the task to work on the identity. The more we get here to the purified compounds, then it's more the marker compound analysis to test the purity and the potency. The target of main interest for cannabis are the cannabinoid metabolites. So in the plant exist mainly the different cannabinoid acids, and during decarboxylation we get then the decarboxylated cannabinoids. THC is very famous because it's the target that has the psychoactive properties. Then CBD is now worldwide a topic because of its pain-reducing properties. There are a lot of more cannabinoids of interest, which we will later see. So we have the three different classes: industrial hemp, medical cannabis and illicit drug. And the industrial hemp is regulated in the European Union. The THC content, so the psychoactive compound, should be less than 0.2%, and in US and in Switzerland the limit is set to 1%. For limit test, HPTLC is a good tool to analyze a lot of samples in one run at the same time at low costs. Then we have the medical cannabis, where we have 3 main different classes. In here, cannabis is regulated and prescribed as a pharmaceutical. So the 3 main types are either it's with a low THC content and high CBD content, or it has a high CBD and a low CBD and a high THC content, or it has both in equal values or equal amount of THC and CBD. For illicit drug, the target of interest is the THC, and there the people want to have THC as high as possible. If we look on the medical use, then a lot of cannabinoids have been analyzed, and the medical purposes have been studied quite well for those. And in here you can see the different medical uses. So especially CBD is used here in this part to reduce pain, for migraine, and in general painkiller. Then we have the mood modulators like THC and other cannabinoids. So if we now look on cannabis analysis by HPTLC, then HPTLC can deal good with the identity, as we know, because it's plant material. And by identity testing, we can analyze, is it the right plant species? Is it the right cannabinoids? But HPTLC can do more. It can also be used for testing the potency and to easily perform a limit test. And it can be used to test the purity of the cannabinoids. That is then more in the application fields to pharmaceutical industry and the dietary supplement, the finished products. But for all of those different tasks, we can have one method to answer these different analytical questions. We can either test the raw materials, or we can test process intermediates, and we can test the finished products. This shows now an example about the developed method, and here you can see the whole process. So with one method we can test the potency and purity. This would be this part with the scanning densitometry, and we can test the identity by visual inspection with the TLC visualizer after derivatization, and structure confirmation can be done in a fast way with the TLC-MS interface by mass spectrometric analysis. Whole procedure can be done, or just parts of it. So we have developed an application note that you can access via the Camag website, download it, and in there the whole procedure is described, and you will have then different conditions for different tasks. Depending on what you're going to analyze, it's either better to perform the analysis on straight phase or on reversed phase. First we will have a look on the straight phase, which is the preferred technique because it's the fastest and cheapest for these purposes. Sample preparation is also described in the SOP, and then depends on if you want to have the whole profile of cannabinoids and cannabinoid acids, or if you just want to have the cannabinoids decarboxylated. So the fast way is that you just have your powdered sample, you mix it with methanol hexane, and centrifuge it and take the supernatant. This can be without further sample preparation applied on the HPTLC blade. For limit test and quantification, we don't have the whole HPTLC process, we just have the steps sample application, development and detection. For this, no derivatization is needed. And if we focus now on the limit test, where HPTLC is really a nice tool because of multiple samples can be analyzed in parallel, you can then have this analysis done in a very short time. 15 samples can be applied on one plate, and if you apply the standard, the set limit in 3 replicates, and the samples, each one in duplicate, then you will have 6 samples per blade. Then after chromatography, this would be now the image, and here you can now see why the image is not sufficient if you directly want to quantify the cannabinoids. The THC is here at this RF position, and the response in UV254 of the image is quite poor. If we scan it at a suitable wavelength at 210 nanometers, then you can see for the THC at this RF position a quite intensive signal. And here, those 3 tracks, 1, 2, 3, that is the set limit. And here, this is our sample that should now be below this intensity. What you can also see here is that we have another big peak here, which is the THC acid. THC acid is during decarboxylation transferred to THC. So for total THC content, you have to quantify this and this peak, or you do the decarboxylation during sample preparation and you will have one target peak to analyze. If you just analyze this, then this would match, then it would say, okay, it's less the set limit. But if you quantify the total THC content, then this sample would fail. So limit test for THC-free cannabis samples. If we have the USA and the Switzerland limit with 1%, then some samples could pass, like in this example, but the same sample with the EU limit could fail. There is not worldwide the same limit set, and depending on your country, depending on your agencies, you have to set the limit and then analyze if your peak is above or below the set limit. On the right side, you have the stack view from VisionCats, where you can confirm that the target compound has the same RF value for the standard and for the sample. So that's the case here, and that's the case here. But here the limit is set to 1%, here the limit is set to 0.2%. Sorry, this is the limit, and this is the sample that passes here because it's below 1%, and here this sample is failing because it's above the 0.2%. This can be done within less than 1 hour. And in addition, you can have the confirmation that it's the right target by UV spectra. During method development, we use the UV spectra mainly to select the right wavelength for each target. And decarboxylated cannabinoids, mainly THC and CBD, can be quantified best at 210 nanometers. And acids, therefore, we have selected a wavelength of 285. So we use this second maximum. If you have method developed for the scanner, then you can have the multi-wavelength scan and analyze in one run all targets at its best wavelength. So our method has then the 210 nanometers and 285 nanometers that we can have the cannabinoids and cannabinoids acid measured in one densitometric measurement. And here is one of the results if we not just do the limit test, if we then do multi-level calibration. So this is now 5-point calibration for THC acid measured at 285 nanometers and quantification of THC measured at 210 nanometers. Then we have in these green rings, we have the samples applied in triplicates, and then you can quite precise analyze those cannabinoids in your cannabis samples. So how long does it take to perform the limit test? The sample preparation is depending on the lab equipment, so I did not take this into account, but I would say usually it can be done in about 20 minutes per sample set. If we just look on the analysis time, then for a separation on straight phase, we have the sample application within about 5 minutes. Then the developing time, it's just 8 minutes, but we have in addition the time for saturation and for drying. Then the scanning densitometry is in about 2 minutes, and evaluation can be easily done in 5 minutes. If we calculate all, in addition also the saturation and drying time, then we have a total runtime of 45 minutes per blade. And now we have 15 tracks per blade, so the runtime per sample is 3 minutes. And I think this is quite fine. If we have for limit test 6 samples in duplicate on a blade, then it's still in a quite good time. Then it takes 7.5 minutes. This is fast. On reversed phase, we need a bit more time, because there the developing time is a bit higher. There it takes about 32 minutes, and then we have a total runtime of 69 minutes per blades, which is then 4.6 minutes per sample. Then also I tried to calculate the running costs. The instruments have to be bought once, and Camag instruments, you know it, they last a very long time. So the investment costs might be high, but then you can run them for many years, and the running costs, they are quite low. For limit test, if we calculate the running cost, then the solvents required per blade is 50 milliliters for the development, so less than 4 ml per sample. We need per sample 5 ml of extraction solvent, and if we calculate an average of the solvent cost, then it's about 0.36 Swiss francs. Then we need 1 falcon tube per sample, and we need the blades. The straight face blades in Switzerland, the costs are about 10 Swiss francs per blade, and if you calculate this per sample, then it's less than a Swiss franc. For RP18, it's 4 times higher compared to the straight face. Then the costs will also increase by a big factor. But in total, on straight face, including the sample preparation, the costs are about 1.4 Swiss francs and 3.4 Swiss francs on reversed phase. So especially here for straight phase, I would say this is quite a cheap analysis. But HPTLC can do more. So these 3 steps, they are for the quantification, either for limit test or for quantification of the content by multi-level calibration. And then we can add derivatization, documentation, and we can do structure confirmation. The start is the same if we do the identification, but then we have 3 additional steps. After derivatization, a blade with separated cannabis samples can look like this. And now this is especially the strength of HPTLC, that you can clearly distinguish the different sample compositions side by side visually. So here we have our system suitability test on the first track with the cannabinoids, cannabinol, tetrahydrocannabinol, and cannabidiol with increasing RF. And then we have here 3 different cannabis types. So this is one that has high THC, where THC and CBD have more or less the same value. Then we have one with low THC and a lot of CBD, and then one that has only THC. The same samples, but then the leaves. Here this is flowers, this is leaves. And then we have here the hemp that has no THC, which would be at this position. Then we can have the same samples, flowers and leaves decarboxylated, And what you can see then in the difference is here on bottom, or in the bottom part of the plate, you have the cannabinoid acids, which are transferred during decarboxylation to the cannabinoid. So here in this one we have THC acid and CBD acid, and after decarboxylation it has a lot CBD and THC. The cannabinoid acids can be analyzed with this straight phase separation, which is beneficial if you want to have the whole sample composition. Oh, sorry. And the decarboxylated are if you're just interested in the cannabinoid itself. So if you're interested in THC content, then maybe it's easier to decarboxylate them and just analyze the one target instead of having the two standards and two calibration curves. But it's depending on the analytical goal. So with HPTLC, you can do a comparison of multiple samples side by side with the software, with a comparison viewer. And these samples, they are now originating from different plates, and they are also of completely different nature. So we have their different cannabis samples, young plants, the harvested plants, hashish sample. We have different process intermediates from CBD extraction. We have cannabis oil, cannabis tincture, CBD cream, so also cosmetic products, and all can be analyzed with the same method. The sample preparation is the same, and then you can easily distinguish them side by side in the comparison viewer. And this is the strength of HPTLC, easily compare samples visually. We have tested 11 cannabinoids and the cannabinoid acids. They are listed here with our ref values. And for the straight phase, some are not well separated, but some are also not a lot in the sample. So this is depending also again what you want to do. If you are interested in certain from other targets, then reverse phase might be the better option. After identification by visual inspection, information with HPTLC-MS. What you need is a pump, can be the HPLC pump that might be anyway in the lab infrastructure, and you need a mass spectrometer. Our TLC-MS interface is then the connection between the pump and the mass spectrometer to elute our target of interest from plate. And this is really an easy step. You just position the head of the interface over your target zone, then you lower the head, the solvent is running through the head and eluting the whole target zone inside of the mass spectrometer. Within less than a minute you get the signal. So here you can see how it works. The head is lowered on the target zone, solvent is going through, and you get the results of your sample. If you elute your reference zone and your sample zone and they match, then you know, okay, it was the right target. You don't have the whole chromatogram like an HPLC, you just get your zone of interest, and this within less than a minute. For HPTLC-MS coupling, for structure confirmation, we have two different methods: an older application nodes with another mobile phase system, where the cannabinoids are, or the most interesting cannabinoids are better separated, but the cannabinoid acids, they are sticking on the application position. So if you're interested in the cannabinoids, then this method is very good. If you are interested in the cannabinoid acids, then here you have the limitations because they are not separated, they are not migrating. For HPTLC-MS, you have to apply twice your sample. For one side, you do the derivatization that you can localize on the underivatized plate your target zone. And then after elution, you get your result and can compare it to your reference peak or spectra and see if it has the same mass or not. With the optimized method for the separation of the acids, you get then the whole sample composition and overview about the cannabinoid pattern and can do the same. So here are the different masses for structure confirmation. And here you can see the overview about all the tested cannabinoids. So in total it's 11. We have the different acids if we look here on the straight phase, CBGA, CBDA, THCA, and the decarboxylated cannabinoids without the CO2. On straight phase, some are not well separated, but you have, after derivatization with fast blue B salt, a color difference. On reversed phase, the separation is better, but the disadvantages here are it's more expensive and you don't have the color difference. So again, depending on your analytical goal, you can either go for the cheap and fast method, or you can go for the better separation with less that it requires more time and which is more expensive. Both can be also optimized if it's a certain metabolite you are interested in. So if you're just interested in THC, then you can also optimize the straight phase, mobile phase, or use the method from the previous application note. And what comes next? Cannabis, always we talk about the cannabinoids, but there are also plant components that are also of interest. We have the terpenes, the terpenoids, and we have the flavonoids. And what is also of interest is the synthetic cannabinoids that are used for adulteration of herbal mixtures. Terpenoids, we did some first tests. We extracted by water steam distillation the fresh flowers, run it with our classical mobile phase for essential oils, derivatized with anisaldehyde, and then you can see that it looks not too bad. This can be still optimized, but this is some preliminary results that are quite promising. Same for the flavonoids from the dried cannabis leaves. Here, extraction with methanol. Mobile phase is a standard system for flavonoids and then derivatized with natural product, polyethylene glycol, and you get then the fingerprints of the flavonoids. Synthetic cannabinoids are used in herbal mixtures, also in the case if it's used as illicit drug. And not every day, but frequently new synthetic cannabinoids are popping up until they are known and regulated. So those are synthesized to put them to herbal mixtures, like spice was quite famous, to have a psychoactive herbal mixture that is not forbidden as long as the synthetic cannabinoid is not forbidden. As long as it's not known, it's not forbidden. And most of these synthetic cannabinoids, they show a fluorescent blue zone without derivatization. So you can screen for them, analyze them by mass spectrometry, and see if there is something added to the herbal mixture. Okay, so we have also done certain marketing activities to distribute our methods. We have presented posters on the HPTLC symposium in Berlin this year, and one on the Cannabis Science Conference in US this year. Then we have the 2 application notes, one on the HPTLC-MS, where you have the separation of the cannabinoids but no migration of cannabinoid acids. And we have our application note with the different conditions, reversed phase and straight phase, depending on the analytical goal, which is more suitable for your analytical task, that describes all options that you have for cannabis testing. So it describes the limit test, it describes the quantification by multi-level calibration, and it describes the identity testing via fingerprint and identity structure confirmation with HPTLC-MS. So here you find all information required to perform this test in your lab. Then we have for THC a short article in the last CBS issue, CBS 119 from September. And we have certain newsletters, CBS Extract and application note newsletters